Hello guys, welcome to Explore Physics. In this video we are starting GR0177 paper from problem number 41. GR0177 from problem number 41. We will solve 5 problems in this paper from up to 45. The first problem is Maxwell's equation can be written in the form given below. If the magnetic charge exists and if conserved, which equation will have to be changed? We have 4 Maxwell's equations and we have to find that which equation will need change if we assume that there is magnetic charge in nature. So we have studied that Maxwell's equations gave relations of electric and magnetic field for moving charge, and Maxwell's equation also does not allow any magnetic charge, the existence of any magnetic charge. Now because we have to assume that there is a magnetic charge, we will use a symmetric equation if for electric charge to the magnetic charge also. So the first equation is the divergence of E, this is equal to rho over epsilon naught, where rho is the charge distribution of electric charge distribution. Now if we assume that there is a magnetic charge distribution too, then the divergence of B will be equal to rho over or rho multiplied by some constant term. The first equation gives the divergence of electric field relating to the electric charge distribution. So this equation is called Gauss's law, and this have nothing to do with magnetic field or magnetic charge. This equation will remain the same if there exists a magnetic charge too. The second equation is del dot B, this is equal to 0. This is 0 if there is no magnetic charge. If we assume there is magnetic charge, then the symmetric equation to this is that one. So this should not be equal to 0. If this should not be equal to 0 if we assume that there is a magnetic charge, then this should equal to del dot B equal to rho m is m for magnetic charge distribution multiplied by or divided by some constant term. Let this is 4 pi. This equation will become like this if we assume that there is magnetic charge, the existence of magnetic charge. So this equation will need change. Now the third and fourth equation. Third equation is the curl of E and fourth equation is the curl of B. This is called Ampere's law. So this is Gauss's law for magnetic field, and this is Gauss's law for electric field. The fourth equation is del cross B, which is known as Ampere law. This equation is known as Ampere law. Ampere law, in a simple case, Ampere law, the curl of B, this is equal to mu naught J. Mu naught J is the current density. So this the second term is called displacement current. This current is also known as Maxwell's correction term. Maxwell have added this term to this the curl of magnetic field. Now this law is complete. This will need no change because there is also a charge density and there is also the change in electric field with respect to time. So the third, if we assume the third equation like this, then the third equation have del cross E. Here is del cross B. Del cross E, this is equal to negative rate of change of time. This is also called Faraday's law of induction. Faraday's law of induction. So this is del cross B, this is del cross E. Here is the rate of change of magnetic field, time rate of change of magnetic field, and here is a time rate of change of electric field. So there should be a term like this. So I assume that there should be Jm. J stand for magnetic charge density. The equation will be likely to partial B partial T plus J m. This is called magnetic current density, and this is 4 pi. I have taken this here, 4 pi or multiplied or divided by some constant term. So this will be like this. We can symmetrically see these two equation, that this is del cross E equal to this del cross E, this is del cross B, this is partial B by partial T, partial E by partial T, J m into 4 pi, and this is mu naught J. So there should be also a displacement current and magnetic current density for in the curl of E if magnetic charge exists. So this equation will also need change. These two equations, Gauss's law, basic Gauss's law for electric field and Ampere's law for magnetic field, these two equations will remain same, but this equation will become Ampere's law for the curl of electric field, and this will become Gauss's law for the divergence of magnetic field. So here this will not be equal to 0, and here this law should have an extra term like this. So equation for second and third will need change. So part E is our right option. Problem 42. Three wire loops are observer are positioned and figure. There are three loops, A, B and a middle loop, and here is observer. We can see in the figure, from the observer point of view, current I flows in counterclockwise in the middle loop. In a middle loop, there is a counterclockwise current in the counterclockwise direction, which is moving toward observer with velocity v. This middle loop is moving toward the observer A with velocity v. The same observer will notice that this observer will notice that which type of current in A and B. We have to find that in which direction the current is inducing in A and B. So we have 5 options: clockwise current in A and B, counterclockwise current and A and B, clockwise in A, counterclockwise in B, counterclockwise in A, clockwise in B, and the fifth option is counterclockwise in A but no current in B. We have Faraday's law of electromagnetic induction, that induced EMF, this is equal to minus d phi by dt. Phi is the magnetic flux, d phi by dt. Phi is the magnetic flux which is responsible to induced electric current or induced EMF. Now this equation states this, that if there is change in magnetic flux through any coil or any loop of wire, there should be induced EMF and induced current. So if this the middle loop is moving, the magnetic field line, because due to this loop, are passing through A and also passing through B. The magnetic field line are passing through A and also passing through B. If it move toward A, then the magnetic field line will increases which passes through A, and the magnetic field lines passing through B are decreasing. So we can see that here the flux is increasing and here the flux is decreasing. So if the flux is increasing, now the negative sign shows that this will change. The negative sign shows that this will resist the induced EMF will resist the original one, means this will resist the change in magnetic flux. Now if this V is moving toward A, then the magnetic field lines are increasing which are passing through A, so the induced EMF will try to resist. So the induced EMF will oppose the original EMF which is in V, which is in the middle loop. So this will oppose, and such that the magnetic field such that the induced EMF or induced current in the loop A will be in opposite direction to compensate the change in magnetic flux. Now if the coil is moving away from B, so the magnetic flux is decreasing in B. So to compensate this decrease in magnetic flux through B, the induced EMF will try to resist this change, so it will compensate such that the magnetic the electric current inducing and this coil and this loop B will be in the same direction to that of the middle loop. So electric current will induced in both A and B, and electric current will induced in opposite direction to the middle one, and induced EMF will induced current will be in the same direction in B to the middle one, because this will resist the positive change and this will resist the negative change. So this will resist the increase and flux, this will resist the decrease and flux. So if we see, then we can say that this is counterclockwise direction, so this will be clockwise. So here clockwise induced in A, and this is counterclockwise, this also in the same direction, so this is also counterclockwise current in B. So option C is our right option. Next problem 43. The component of orbital angular momentum L are Lx, Ly and Lz. Satisfy the following commutation relation. These are the commutation relation between any two components of the orbital angular momentum. The commutation between x and y equal to iota h cut z, and Lz is equal to Lz is equal to iota h cut Lx, and Lxz this is equal to iota h cut Ly. Now, what is the value of the commutator for Lx, Ly and Lz? We have to find the value of this commutator using these three relations. First of all, we know that the commutation between any two components, this is the negative if we interchange their places. A B commutation, this is equal to minus BA commutation, and so if we take this commutation as Lx, Ly commutation Lz, this will become equal to minus of Lz, Lx, Ly. So first of all, we are using this relation for the commutation. The second, we also know another commutation relation as that B commutation AC, this is equal to B commutation with AC, this is equal to A and to B commutation C plus B commutation A, this is equal and to C. So this is the next second commutation relation, general commutation relation. We will use this one to expand this. So here this is equal to B, and Lx this is A, and Ly this is C. So if we use this commutation relation, we can expand this commutation such that minus n2, this is Lx is A, so Lx n2 Lz commutation Ly plus, we can also write that Lz n2 commutation Lx n2 Ly, so into minus. Now using these relations, we know that Lz Ly, Lz Ly, Ly and Lz, this is equal to iota h cut Lx, but if we replace their, then this will become Lz Ly, this is equal to minus iota h cut Lx. If we use this relation AB, this is equal to minus BA, Ly Lz, this is equal to Lz Ly, so we will multiply minus with it. So we can write that minus into Lx and 2 minus iota h cut Lx, we can write like this, plus Lz Lx, this is directly equal to iota h cut Ly and 2 Ly, this one, so we can write here. Now this is equal to minus n2 minus iota h cut Lx square plus iota h cut Ly square, multiplying these two terms. So this, if we multiply minus, then this will become iota h cut Lx square minus iota h cut Ly square. So if we take common iota h cut, then this will become Lx square minus Ly square. So this will be the value of this commutation relation, this commutation, if we use these three relations. And these are the commutation laws that the commutation, interchanging the commutation will equal to the negative of that commutation. So we can see that this is an part D. So part D is our right option. Next problem 44. The energy eigenstate for a particle of mass m and a box length L having a wave function size equal to 2 over L sin n pi x over L and energies En is equal to n square pi square h cut square over 2 ml square, where n start from 1, 2 and so on, at time t equal to 0. The particle is in state described as, this is the state of the particle. This is a particle, means there is this is the linear combination of three states, psi phi 1 2 phi 2 plus 3 phi 3. Which of the following is a best possible results for the measurement of energy for state psi? Now we can see that this is a one-dimensional box. This is a one-dimensional box, yeah, square wheel. This is a square, this is a one-dimensional square wheel, and this is the function for the square wheel wave function, and this is a function that describe these three states. This is a phi n of x, and this is phi 1, phi 2 and phi 3, linear combination of these equations psi. And we are given that the energy of this, the eigenstates are En, this is equal to n square pi square h cut square over 2 ml square. The following, which of the following is best possible results for the measurement of energy for the state? So we have to find the energy for the state. The formula for energy of the states are given, is given in this problem. So we have nothing to do with this and this. We only take this formula and we start to find the energy relations. So if the formula is given is n is equal to n is equal to n square pi square h cut square over 2 ml square. If I put n equal to 1, then this will become n e1, n square will become 1, so this will become pi square h cut square over 2 ml square. Now if I take En, this is equal to n square pi square h cut square over 2 ml square. We can see that this is equal to E1, so En, this will become n square E1. So the relation for energy of the states for each state will become En, this is equal to n square En, this is equal to n square E1. So we can see from this that the possible energies are E1, then if n is equal to 2, then this is 4 E1, then if n is equal to 3, this is 9 E1, 16 E1, 25 E1 and so on. So we can see from this that 9 E1 is a possible energy out of these all. So part D is our right option. Problem number 45. Let n, state n, represent the normalized nth energy eigenstate of one-dimensional harmonic oscillator H. The energy Hamiltonian operator, energy operator is given h cut n2 n plus 1 by 2 if psi is a normalized ensemble state that can be expanded as a linear combination of, this is the linear combination of these states 1, 2 and 3 of the eigenstates. What is the expectation value of energy operator? We have given that we have one dimensional harmonic oscillator which energy operator Hamiltonian is given as, and this one dimensional harmonic oscillator function psi can be written as the linear combination of these states, and the psi is normalized, so we have to find the expectation value of H. The formula for expectation value is psi steric inner product of with psi, this is equal to this is equal to the expectation value of H, which is energy operator. Now we have to find the product of these psi with psi and H, and we can see from the problem that H, this inner product with n, any state, this is equal to H cut omega and to n plus 1 by 2. So this is a constant value, this is a constant value. We will take out this and we will multiply these psi with psi, and which is the same function, so we will square their states only. Now for if n is equal to 1, then if n is equal to 1, so the product of H with 1, this will be equal to H cut omega into 1 plus 1 by 2, this is equal to 3 by 2 H cut omega. If this is 2, then this is equal to H cut omega into 2 plus 1 by 2, this is equal to 5 by 2 H cut omega. And if the state n is 3, we have 3 state 1, 2 and 3, then this is equal to H cut omega into 3 plus 1 by 2, this is equal to 7 by 2 H cut omega. Now we have calculated values of a Hamiltonian operator with any nth state. If the state 1 is then this is equal to 3 by 2 H cut omega, H2 this is equal to 5 by 2 H cut omega, and this is equal to 7 by 2 H cut omega. So if we are coming to find the average, the expectation value of Hamiltonian, then this will be equal to the product of these two function into multiplied by these values. So for this state I am writing that 14 square root, this is for 1, this is, and 1 over 14 square root, this is for this function, and 2 constant value of H, this is 3 by 2 H cut omega, and 2 their states, the product of their state 1, inner product of 1 with 1 plus. Similarly for the second state we will take that minus 2 by 14 square root and 2 minus 2 by 14 square root minus 2 by 14 square root and 2 5 by 2 H cut omega plus, and 2 this will be the product of 2 with 2 plus. If we multiply the third stage, then this will be equal to 3 by 14 square root and 2 3 by 14 square root plus and 2 7 by 2 H cut omega, and 2 the inner product of 3 with 3. Because these are normalized in the eigenstates are orthonormals, so the product of 1 with 1 will be equal to 1, 2 with 2 will be equal to 2, and 3 with 3 will be equal to 1. So this goes to 1, this also goes to 1, and this also goes to 1. So we have only the constant term which are multiplied, and we will multiply, then we will add these term. If I multiplied these, then this become 3 divided by 14 square root 14 multiplied by 2 28 H cut omega, plus if we multiply this minus 2 into minus 2 minus plus 4 multiplied by 5 20 divided by 14 square root into 14 square root into 2, this will also become 28. Now if we, this is equal to H cut omega, plus if we multiplied these, then this is 9 and 9 multiplied by 7, this is equal to 63 divided by 28 into H cut omega. If we add up all these, then 28 is LCM, 3 plus 23 plus 63, this is equal to 86 divided by 28 H cut omega. If we simplify this, then divided by 2 both, then this is equal to 43 divided by 14 H cut omega. So this will be the expectation value of the energy operator H, which is a Hamiltonian for this one dimensional harmonic oscillator. So part B is our right option. Friends, if you understand that these videos are helpful to you, then please like, subscribe and share with friend. Thanks.